Hello everyone, my name is Caishen Chen. I'm a student from East China Normal University. The research direction of our team is spatial temporal determining, and I'm going to present a research about road closure detection based up on multi-feature fusion. I will go into detail through the following five aspects. Firstly, it's a part of motivation. With the widespread uses of GPS equipment, the residents rely more and more on applications of map navigation. As one of the main reasons caused the change of road network, road closures come up very frequently due to the events like traffic control, bad weather, and road construction. Delayed or missed detection of road closure not only create inconvenience for travel, but result in great economic losses of road users. In recent years, the exist map update research focus more on the detection of the missing roads, less on the detection of road closure events, and some researchers also regard road closure as a type of traffic anomaly and detect it according to abnormal changes in traffic situation within the regions. The aforementioned methods identify the road closure in terms of the plunge in traffic flow, but which may lead to error detection of traffic jams having the same property. In addition, they are unfit for detecting one-side closure of two-way road and the closure in the middle part of the road. In the left figure, one side of the road is closed, but the other direction lane can still be passed normally. In the right figure, the closure in the middle of the road makes the vehicles have to take a U-turn towards the original road. In both cases, the traffic flows of this closed road do not drop into zero. Some closure features need to be considered, like traffic flow, turning volume, and U-turn frequency. Then let me introduce the framework. Firstly, we import a road network from OpenStreetMap and trajectory data from three open datasets. Then we divide the whole detection framework into two main parts: offline road closure feature modeling and online road closure identification. In the first part, there are grading, road correlation, mining, and closure feature extraction. The second part includes the closed-grid candidate screening and road closure detection. In the offline road closure feature modeling, we first split the region into a set of grids and build the inverted index based on grids number, trajectory, and road network data. Then we use hidden Markov-based map matching algorithm to obtain the matched road sequence. The every road pair in sequence can count the road correlation. Road with maximal correlation is regarded as a strongly correlated road. For any two-way road, there is a strongly correlated road in each direction. Finally, we extract the three closure features. There are grids, traffic flow, strongly correlated roads turning volume, and U-turn frequency. By inverted index, we can quickly get trajectory data within each grid and the number of the vehicles in each grid as traffic flow. Turning volume we can obtain through the matched road sequence and only need to keep strongly correlated roads because comparing with other related roads, the changes in turning volume of strongly correlated road after closure are more dramatic. It is enough to capture traffic changes during road closure. Then we propose an algorithm to obtain the U-turn trajectory. At first, we get clustering results through the turning point DB scan method, then represent the clustering results in the form of a convex hull. and if the angle gap between the first point of a certain trajectory entering the convex hull and the last point leaving the convex hull is greater than the preset angle threshold, the trajectory is judged as a U-turn. Through offline road closure feature modeling, we can get the road adjacency matrix, grid closure feature matrix, and road closure feature matrix as model input. In online road detection, there are two stages: closed grid candidate screening and road closure detection. The target of firstly screen the road closed grid candidate is reducing the cost. Due to that, it does not in placement map matching at the beginning of the online detection. We use deep learning technique to predict the value of closure features for each grid or road in the current time period instead of using their historical normal values. Based on that, we compare true values with predictions to find the grids or roads that have significant difference of road closure features in the current time period. This is the classic time series anomaly detection method, and we adopt two different combinations of neural network models to extract spatial temporal dependence from two region levels. CN and GCN are used to capture spatial dependence between grids and rows, respectively. LSTM is used to capture temporal dependence. Here is the evaluation. We choose the dataset from three major cities from evaluating our experiments, which can represent a complex road network of most cities in China. It contains the taxi trajectory dataset of Shanghai, Beijing, and Chengdu, and there are time coverage, sampling, and the number of trajectories. The purpose of the choosing these three cities is to cover more traffic scenarios in different places, and the parameters of detection models can be more applicable to other different cities or countries. To evaluate our method, we compare with three approaches to verify the effectiveness and efficiency. TB1 aggregates rows with a node degree less than 3 into a road set and determines the road closure based on the changes in the ratio of the road flow rate to the road set flow rate. TB2 introduces the definition of the betweenness centrality to indicate the importance of roads in the cold start phase and determines the closure based on the time interval of the vehicle passing through the road. PB is the statistical based method to determine road closure by establish a Poisson process and run a p-value test on a chi-square distribution. In the left figure, we can see that our method RCDM is optimal in the measurement of these three evaluation metrics. And in the right figure, when the number of trajectories is small, the gap between RCDM and the baseline methods is not obvious. But when the number of trajectories continue to increase, the execution time of RCDM is much lower than the comparison algorithms. It shows that our method has better performance. Then let's take some case studies. Here are two real closed events. The left is one side closure of two-way road and the other is road closure in the middle of road. Because our method combines the turning volumes and the turning frequency, we can successfully detect both of these cases. And here are the change trend of these two features. During the detection stage, we additionally find two special types of closures. One is periodic closure. There is a flag rising event at Tiananmen Square in East Chang'an Avenue. It regularly caused a significant drop in traffic flow at about 6 o'clock in the morning because of the road closure. In addition, some trains will pass through a few urban roads at a fixed time period every day, which makes this road closed for a short period of time. The other is a closure caused by the merging lanes. It is a particular situation of one-side closure. For some cases of one-side closure, we observe that turning volume of strongly correlated road has not declined largely, but their trajectory have obvious deviation compared to historical normal route because the original two lanes are changed to a single lane, which leads to the trajectory leads towards the opposite side of the road. And we calculate the offset of the trajectory to detect this closure. Finally, its a conclusion. We propose RCDM to detect road closure based on multiple features, and we design a strategy of closed-grid candidate identifying first and then road closure detecting. Then we use deep learning technique to predict the value of road closure features in online detection. In the future, we will further tackle the issue of semantic annotation for road closure events to ensure high quality of navigation service.